All right, I'm back. We're going to be on page 298. But what I think I should do right now is I think I should show you a function that is continuous everywhere, but is not necessarily differentiable. So the function that we're going to look at is not that difficult a function to deal with. It's actually going to be f of x is equal to, is that big enough? I don't know. Let me make this bigger. Let's see. I'm gonna zoom in. So you can't see what I'm doing. I'm zooming in. I'm zoomed in 270% right now. I'm gonna say that f of x is the absolute value of x. Okay, so we know that the absolute value of x can be written as, so the absolute value of x can be rewritten as the opposite of x when x is less than or equal to 0, and x when x is greater than 0. Or you can put the equality on either of them. It doesn't really make a difference, right? So if I wanted to prove that f of x is continuous, I would just need to show that the limit equals the value of the function for all x. Well, when you're just thinking about x and you're just thinking about negative x, those are obviously continuous. The only place there could be an issue with continuity is at x equals 0. So if I wanted to show that this is continuous, so is it continuous? I mean, it is, right? And you know that, but I need to show that. So I'm going to say the limit as x approaches 0 from the left of f of x. So 0 from the left, that means like -1, -0.5, negative whatever, negative values, right? So this will be the limit as x approaches 0 from the left of negative x. But that limit is definitely 0. Okay, so we're good so far. Now I need the limit from the right. The limit as x approaches 0 from the right of f of x is going to be the limit as x approaches 0 from the right of, so to the right of 0 is 1, 0.5, 0.1, positive values. So that's going to be the limit of just normal x, which is also 0. So we know that the limit as x approaches 0 of f of x is equal to 0. All right, by definition, f of 0 is also 0, right? Because we're supposed to use the negative x branch when x is equal to 0. So we know that f of 0 equals 0. So then we can say f of x is continuous. This is not a great use of space, but that's okay. At x equals 0. Okay, so we proved it's continuous. We already knew it was continuous, but like, you know, you do things. All right, so can we find the derivative at x equals 0? So what I'm going to do is I'm going to copy this over, paste it. Okay, so is it differentiable at x equals 0? So what does it mean for it to be differentiable? It means that the derivative exists. If the derivative exists, then that means, so is it differentiable? So does the limit as, so at x equals 0, so everywhere except at 0, this is going to be fine, right? Because negative x is a line, it has a slope of -1. Derivative exists everywhere. X is a line, it has a slope everywhere, it's always going to be 1. So does the limit as x approaches 0 of f of x minus f of 0 over x minus 0 exist? That's the question that we're trying to answer. Does this exist? All right, well, we can do that. For that limit to exist, it means the limit from the left and the limit from the right both exist. So the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0 will be equal to, so what is to the left of 0? So this is, it's always very similar to when you're dealing with continuity, which is why I started with that. So to the left of 0 are negative numbers, so we replace f of x with negative x. F of 0 is 0, so minus 0 over x minus 0. If we simplify this, it actually just simplifies to -1. So far, okay. The limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0 is going to be the same as the limit as x approaches 0 from the right of what's to the right of 0, 1, 0.1, positive values. So it's going to be, you replace f of x with just x, and then minus 0 over x minus 0. This is definitely 1. Okay, so because we got different limits, therefore, the limit as x approaches 0 of f of x minus f of 0 over x minus 0 does not exist. What does that mean? That means, so that implies f of x is not differentiable at x equals 0, which also means f of x is not a differentiable function. If there's any point in the domain of the function where the derivative doesn't exist, the function is not a differentiable function. So the absolute value of x is the classic example. Let me show you visually what's happening there. So I don't even know what color that is, but here's the absolute value of x. Anytime a graph has a sharp turn, so a sharp turn or a corner is another way of saying that. Sharp turn or a corner, the derivative is going to fail to exist. It is not differentiable at a sharp turn or at a corner. Okay, so what does this have to do with the notes? Well, let's go back to the notes. How do I go back to the notes? Let's go back to the notes. All right. This page contains one of the most important things that you will run into in the early outset of calculus, and it is this. Differentiability implies continuity. If a function is differentiable at a point, it is definitely continuous at that point. So differentiability implies continuity. What does the absolute value of x have to do with that? The absolute value of x is continuous, but not differentiable. So continuity does not imply, this should be in another color, it's that important. Let's see, here we go. Continuity does not imply differentiability. So you should always be thinking of the absolute value of x when this comes up. Differentiability implies continuity. Continuity tells you nothing about differentiability. Absolute value of x is the best example of that. And so that's why I want to run through that whole thing. It's kind of long-winded, but I didn't really talk too much. I just did the math, at least. So continuity does not imply differentiability. Differentiability does imply continuity. If a function's continuous at a point, we don't know anything. If it's differentiable at a point, we definitely know that it's continuous at that point. So this is like the all squares are rectangles, not all rectangles are squares. All horses are, I don't know, all horses have 4 legs, but not all 4-legged things are horses. I know that now there are I think there are probably some 3-legged horses out there, but they used to just basically shoot horses when they broke a leg because they kind of can't heal because they just weigh too much and they have these pencil thin legs. Whatever, not really the point. So this is a big idea. It's so big. Let's highlight around the edges. Let's highlight it in this color. Here we go. Big deal. Okay, so differentiability implies continuity. There's a proof of it here. I don't find that the proof really does anything for people, so I'm not really going to walk through it too much. You can give it a read through. I will point out that at the bottom of the proof is a weird thing. So this right here, when you see the limit as x approaches a of f of x minus f of a equals 0, that's a weird way of writing that a function is continuous at a point. It's a very College Board way of writing it. They love to write that. Okay, so why is this equivalent to a function being continuous? Well, f of a is a number, so the limit as x approaches a of f of a is just f of a. So this is really the limit as x approaches a of f of x. That could be in parentheses, and then just minus f of a equals 0. But then you can move f of a to the other side. So I don't know where I'm putting all of this. Let's go up here. The limit as x approaches a, This actually, I think that this is the most important thing that you actually get out of this proof, is that there's another bizarro way of writing continuity, f of a, which is the third part, right? So you're saying if the limit as x approaches a of f of x equals f of a, then they both must exist, which means f of a exists, the limit exists, and you just said that they're equal. There's a weird way of writing continuity. So you will run into this kind of a lot. Weird way of writing continuity. Strange. It's a very weird way of writing. I think it's the most important part of this proof, is that you see that way of writing continuity. All right, so I'm going to stop this here. No idea how long this video is. I'm going to come back in the next video and like do some more things about like differentiability and like how it looks on a graph. And I will see you then. So hope you're finding these helpful. Hope they're kind of interesting. Hope it's like, I don't know, something for you to do, right? So you can go back, you can rewatch, whatever. See you in the next one.